Hello, this is Mr. Collier, and today we're doing some induction divisibility proofs. Okay, so in this first example, we've got show that 4 to the power 2n minus 1 is always divisible by 5. This is another way to write that. This means 5 goes into 4 to the power 2n minus 1, so it means the same thing as divisible by 5. Okay, I'm going to start with, and this should probably say n is in z plus, or sometimes it says n is in n, which is natural numbers starting with 0. So let's start with 0. For n equals 0, we have 4 to the power of 2 times 0 minus 1, which equals 0. And 0 is divisible by 5. So therefore it's true for n equals 0. Next case, n equals k, assume that 4 to the power 2n minus 1 is divisible by 5. Okay, another way to write that, k, this should be a k. Another way to write that is 4 to the power 2k minus 1 equals a multiple of 5. Okay? So k and a are integers. Okay, so now we go to the next step. We have, we start with the k plus 1 substituted for n. Okay, and we'll simplify the exponent here. Now, if we have this, we can split this up into 4 squared times 4 to the power of 2k minus 1, right? We can split that up that way. And then what we have is we have 4 to the power 2k, which we can substitute with 5a plus 1 using this equation right here. So we have 4 squared times 5a plus 1 minus 1, and we just use our assumption, so I'm going to write by assumption here. Okay, and what we do is we'll simplify this and we'll show this is divisible by 5. So this is 16 times 5a plus 16 minus 1, which equals 16 times 5a plus 15. And we can factor out the 5, and we have 16a plus 3. Okay, so therefore it's true for n equals k plus 1. And then we can write it's true for n equals 0. And if it's true for n equals k, then n equals k plus 1 is also true. Therefore, it's true for all n. So for 4 to the power of 2n minus 1 is divisible by 5 for all n in the natural numbers by the principle of mathematical induction. Okay, next we have a slightly different divisibility question. So let's start with the base case. N equals 1, and that means 1 cubed minus 1, which equals 0, and 0 is divisible by 6, so it's true for n equals 1. Let's go to the n equals k, so assume that 6 goes into k cubed minus k for some k in the integers, positive integers. Okay, that means that k cubed minus k equals 6a for some integer a. Okay, next we go to the n equals k plus 1 case, and so let's plug in k plus 1 cubed minus k plus 1. This is going to be cubic, so I guess, yeah, we can simplify this. Okay, let's expand this. So we have k cubed plus 3k squared plus 3k plus 1 minus k minus 1. And notice here we have k cubed and we have a minus k. So we can take that and substitute 6a. So we can say 6a plus 3k squared plus 3k. The ones cancel. And this is 6a plus 3k times k plus 2. So if we look at this closely, now this is a 3, so it's not divisible by 6, but this is a, so this should be a 1 in here, first of all. That should be a 1. So this is divisible by 3. This is a product of two consecutive numbers, so this is even. Okay, so we can write this as 6a plus 3 times 2b, or some integer b. Okay, so then we have 6a plus 6b, so this is divisible by 6. Okay, this is divisible by 6, therefore it's true for n equals k plus 1, and then you need to write your statement at the end. Okay, let's look at another example. Let's start with the base case, n equals 1, and you're going to have 7 minus 4 minus 3, which equals 0. 0 is divisible by 12, therefore true for n equals 1. So for n equals k, assume 7 to the power of k minus 4 to the power of k minus 3 to the power of k equals 12a for some positive integer k and some integer a. Now for the n equals k plus 1 step, let's consider when n equals k plus 1. Okay, so we have this, and let's simplify this to 7 times 7 to the power of k minus 4 times 4 to the power of k minus 3 times 3 to the power of k. And now we can substitute in for the 7 to the power of k. You can write 12a plus 4 to the k plus 3 to the k. If you just rearrange this up here. And then we still have the minus 4 times 4 to the k minus 3 times 3 to the k. So this is, I missed the a here. This is 7 times 12a plus 7 times 4 to the k plus 7 times 3 to the k minus 4 times 4 to the k and so forth. So this is already divisible by 12. Let's just keep it like this. You don't even need to multiply it. Here we got 7 minus 4 is 3, so you can have 3 times 4 to the k. And then we have plus 4 times 3 to the k. Alright, so we want these things to be divisible by 12. We have a 3 here, which is not quite 12. But notice if you do 3 times 4, you get a 12. So we can make that happen. We can do 3 times 4 is 12. Okay, so this is the same as 12 times 4 to the power of k minus 1, right? Okay, because 4 times this gives you 4 to the k. Okay, we can write this as 4 times 3 times 3 to the k minus 1 as well. And then that becomes a 12, right? This is 12, this is 12, this is 12, so we can factor it out. And the whole thing is divisible by 12, therefore true for n equals k plus 1, and then you need to write your statement at the end.